In this video, we will be discussing resting membrane potential and action potential. More specifically, we'll look into the different parts of a neuron, depolarization and repolarization on a zoomed-in axon, and then we'll look into hyperpolarization and then tie everything together. Before we talk about the different parts of a neuron, let's discuss the difference between action potentials and graded potentials. Action potentials and graded potentials can both be thought of as messages to be sent through a part of a neuron. Graded potentials are created through incoming signals, mainly from other neurons. The strength of a graded potential can vary, and decreases in strength as it travels down the dendrites, which we will discuss later. Once these graded potentials travel to their destination, the axon hillock, they tell the axon hillock to send an action potential. An action potential is therefore created by adding up all of these incoming graded potentials. These varying sizes of graded potentials coming into the axon hillock cause the polarization of the area to become more and more positively charged. The resting membrane potential of a neuron occurs when the neuron isn't doing anything. No messages are being sent and it's just resting. At this state, the neuron's charge is negative 70 millivolts. But as these graded potentials come in, an action potential will not be created until the cell has reached negative 55 millivolts. This number can be referred to as the threshold. Only after reaching negative 55 millivolts, an action potential will be sent down the axon, telling the axon terminals to release neurotransmitter. The strength of this action potential, unlike in a graded potential, will always be the same. There are a few basic parts of a neuron we need to know in order to understand how the action potentials and graded potentials work. The dendrites, as we mentioned previously, receive incoming signals from other areas. They create graded potentials that travel into the cell body, which resembles any other cell in that it has a nucleus and other organelles. We just left them out of this drawing. As we were talking about graded potentials, we also mentioned the axon hillock, which serves as a gate between the cell body and the axon. It tallies up all of the graded potentials and produces action potentials to be sent down the axon. The axon is a long tail-like structure that sends messages in the form of action potentials down to the axon terminals. The messages travel by using voltage-gated channels, which line the axon. We will discuss those in more detail later. Once the messages reach the end of the axon, it goes to the axon terminals. The axon terminals then release neurotransmitter, which are chemicals hiding in the little ventricles. Neurotransmitter is released through exocytosis. During a resting membrane potential, there are more positively charged ions outside the neuron than inside, giving a neuron a relatively negative charge of -70, as we mentioned earlier. This number changes when action potentials come into play. During an action potential, the axon is depolarized, meaning it gets more positively charged. Now here you see a zoomed-in version of an axon. On the axon, there's various voltage-gated channels, which in our case are either blue or orange. Orange for a potassium channel and blue for a sodium channel. As the name implies, voltage-gated channels open and close as the voltage changes. So as that action potential travels down the axon, sodium channels open and let sodium in. As the positively charged sodium ions come into the axon, the charge of the axon continues to go up past the threshold of -55 millivolts that we talked about earlier. Watch the sodium ions move in. As you see all of this positive charge come in, you can see how the overall number would continue to climb. After reaching about +30 millivolts, the axon reaches its peak and repolarization begins. During repolarization, as you would expect, the neuron starts to become negative again in order to return back to that resting membrane potential. Unlike depolarization, where the sodium channels open, now the opposite's going to happen, and the potassium channels, which are in blue, now open, and those positively charged potassium ions that were in there from the get-go start to leave the neuron. Watch this animation to see how it occurs. Now, we are human, and neurons aren't perfect. These potassium channels close a little slowly, so even once the -70 millivolt resting membrane potential level is maintained again, potassium still keeps leaving the cell. This phase is known as hyperpolarization. Luckily, the channels eventually close, and the sodium-potassium pump moves the ions back to where they should be. Now, let's tie all of what we learned together with this graph, which shows the change in millivolts during the different parts of an action potential. On the x-axis, we have times in milliseconds, and on the y-axis, we have the millivolts. The graph starts off with the neuron in a resting state, which, as we learned, is a static -70 millivolts. And as the graded potentials start to come into the neuron from the dendrites, this number becomes more and more positive. Once the axon hillock reaches that -55 millivolt magical number of the threshold, an action potential starts going down the axon, opening more and more ion channels, letting in tons of positively charged sodium ions, making the neuron rapidly more positive. This portion is referred to as depolarization. Then the neuron reaches a peak around 30, and repolarization begins. The neuron becomes increasingly negative again, and ions start to leave. Hyperpolarization occurs when that graph makes the dip below the resting state, which is fixed later with the sodium-potassium pump. Because hyperpolarization is even more negative than normal, firing another action potential is increasingly more difficult, since you would need more graded potentials to make it back up to that -55 again. Since, at the bottom of the hyperpolarization dip, you're pushing around -90, so you need even more positive graded potentials to build back up to have another action potential occur. I mean, that's a charge of a 40 difference instead of 20. So you're going to need some extra graded potentials. Hyperpolarization gives the cell time to recharge between action potentials for that very reason. After hyperpolarization, the cell goes back to the resting state and waits for the cycle to start all over again.